Today I'm gonna do a small explanation and presentation on logistics and shipment models. And these are a part of operation and supply chain analytics, which comes under the domain of business analytics. So first thing is, let's understand some background information. And first thing is, what is logistics? So the art and science of obtaining, producing and distributing the material and the products in the proper place and in the proper quantity. So you source the raw material, you do the production, and then you distribute it, be it a semi-finished good or the finished goods, and you put them in proper warehouses, and then you deliver to the retail stores in proper location and in proper quantities. So that is the domain of logistics. And let's look at what are the right transportation modes. This is a part of background. So you have different transportation modes that we are all are aware of. For example, you can send your goods via railways. You can send it through steamers and ships. You can send it through trucks or the carriages on the highway. That's a road transportation. You can send the goods via air in the aeroplane. You can send the liquid or gas products via pipeline. Or if it's a small quantity, the retail distribution, it can happen through the hand delivery mode. So now what to choose when? So when volumes are high, cost of individual cost per unit is low. So we will prefer goods like ships for high volume, low cost, and also one example is like, depending on the nature of the goods, you can choose pipeline also if it's a liquid or gas, and the road transportation comes in middle. But when it's a low volume, yeah, and costs are high, you prefer hand delivery. Similar, it goes for air. Normally when volumes are relatively less and cost is very high, expensive items, you send it through the air. So now we know the different modes of transportation and when is logically possible to use when. Normally cost of transportation varies and depending on the volume that you, so depending on the volume and the transportation cost and the feasibility, you choose the right mode of transportation. So one of the key topics, now I come to the main topic. The key topic of today's discussion is around factory or warehouse locations. So normally we have three methods, and then when we talk about service facility, we have a fourth method. So first method, when we decide about the location of a factory or a warehouse for storage and inventory taking. So we have these three methods. First method, we call it factor rating method. Second method is centroid method. Third method is shipment method. And fourth method normally used for service facility is multivariate linear regression. So we discuss one by one the different methods for deciding on the location of factory or a warehouse. So factor rating system, which is relatively easier and it's most widely used. So we decide on a list of factors. You can see here like fuel availability in the region, power availability in that particular area, labor, climate, living condition, transportation, water supply, climate, supplies, and the taxation of that area. So you decide on the scale, and then you rate different. So list of factors are developed, and then range of possible point is assigned to each factor. So you look at the range here, like for fuel 0 to 330, for power is 0 to 200, for labor availability it is 0 to 100. Then suppose you have 5 sites, then you rate all these 5 sites against these factors, and then you assign them the points for each site. Then you, for each site, the sum of assigned points for each site are computed, and then the site for these factors, the one with the most number of point is selected. Sometime you, suppose if when you select the 0 rather than 0 to 330, 0 to 200, you select all the ranges, say suppose 0 to 10. For example, suppose all of them are this range, all of them are here 0 to 10, then in that case you assign the weights. So different weights are assigned: W1 maybe for fuel availability, W2 for labor, climate. So one, rather than different having range of possible points, if suppose you want to decide on the same range, then you can assign different weights to different factors, and then you multiply weights with the assigned points for each factor, then and you do a summation, and the site with the most point is selected. The site out of 5 sites, the site which has the maximum point, you select it as the location for a factory or the warehouse. Now second method is a centroid method, and you use it for locating single facilities that consider existing facilities, the distance between them, and the volume of goods shipped from them. So assume inbound and outbound transportation costs are equal, and it does not take into consideration special shipping cost for less than full load. And this methodology involves formula used to compute coordinates of two-dimensional point x and y that meet the distance and volume criteria here. So here basically it's about distance and volume, and you calculate x coordinate and the y coordinate. Suppose you plot all the possible existing facilities and the one that you're interested in, all of them are put on two-dimensional xy map, and once you have the coordinate of existing facility, then the volume and the distance, and the formula for coming up with the coordinate of this facility of interest is x coordinate for this centroid is its summation of distance from the existing, suppose it's location 1, distance from location 1, and then the volume that is transported between them, then the plus distance to d2 from the second location, and then volume 2, similarly like on depending on number of existing facilities, and then you divide it by the summation of the volume that is transported between them. Similarly for y coordinate, that then it is a distance in terms of y coordinate, distance between this single facility of interest d1 into, says, and volume supposed to existing site 1 is v1, so d1 plus v1 plus d2 plus v2, so on, divided by summation of volume. Suppose there are two location only, then v1 plus v2. So Cx become the centroid x coordinate, cy is the y coordinate. Sorry, spelling mistake. It's a y coordinate of centroid. Dx is the x coordinate of the is location. Diy is the y coordinate of the existing location. Different, and vi is the volume of good move to and fro from the ith location. Now let me explain this using a example. It will be much more clear to you. Let's take this high octane petrol company. So this is a case of high octane petrol, and this company need to locate an warehouse. So this is a warehouse, and this warehouse has to be between its refining plant in Long Beach and its major distributor. So between the distributor and the refinery, they have to figure out the warehouse location. So they decide that okay, let's look at the centroid method. So okay, so where is the refining plant? What is the coordinate? Is 325, diy is 75, and vi. So you can see here for this warehouse, x coordinate become 325 into 1500, that is volume, plus second distributor, the x difference between the x coordinate 400 plus multiply 250 plus 450 into 450 plus 350 into 350, 25 into 450, and the summation of the volumes that shift between them, and it becomes x coordinate become 307.9. So we can roughly say it's a 308. Similarly, the coordinate y coordinate is, yeah, so yth coordinate of the I location and then multiplied by the volume. So normally you will ask me what is this volume shift between, in this case it's a volume between refinery and that particular distributor, and here 75 is the difference between the y coordinate, so 150 and then volume and divided by summation of volume. So you see both of these numbers are 3000, both the numbers are same here, but the x coordinate summation and the y coordinate dix into vi or diy into vi, that is different between of them. So y coordinate come out to be 217. Now let's look at it and do, so here you may be a little bit confused. Now let's look at this in two dimensional xy map so that things become clear to you. Okay, so there here is a Long Beach, and these are the different distributor. Actually, I did not show you this XY plot before, otherwise things would have been much more clear. And this is the 308 and 217. So we just go back, 308 and 217. These are the coordinate I shared with you. And now you will ask me what is this 325, 400? And then you can easily see here. This is 325. This is 400. Yeah. And this is 450, 350, and 25. 450. So these are different. Yeah, you can see easily here. See here, these are the x coordinate of different distributors in the factory, and then you multiply it by the volume that is transported between them. Yeah, and then you can similarly for y coordinate, these is the y coordinate, like for example this is 75, this is 150. So this is 75 for y coordinate and this is 150. So on. So I think it's become clear to you how to use. So this is basically a centroid they figure out the xy coordinate of the centroid, and this should be the proper place. Then they look at the geographical map and then figure out what is the city or the town that is as near to the centroid where they can put their warehouse, they can locate their warehouse, or the for this petroleum company their holding point. So now let's look at the third example, and which is I think should be the major discussion point today from the analytics point. So normally when you talk about models, there are three type of model. One is descriptive, like which tells what has happened; predictive, which say what could happen. So there's, like, for example, forecasting is one good example, and prescriptive, what should we do. So if you know something gonna happen, then what is the best solution? And one ship perspective model is shipment and transshipment. So in this case, you look at shipment of goods from plant to warehouse. So from plant to warehouse, or to distribution center, or to other destination, and includes organization, intra-organization and inter-organization shipments, and count for specific part of cost. So basically we are in this case, when the goods are transported from plant to warehouse or to distributors or to the final customer, there's a distance involved and there's a cost involved, and we are trying to minimize the total cost of the shipment. So the problem is around how much goods to be shipped from which plant to which warehouse, or from which warehouse to which distributor, so that our total cost of transportation is reduced. And normally shipment models are represented in network diagram like nodes and arcs. And general formula for transportation, this is optimization problem, like a perspective. So this is our general formulation. We want to minimize. This is the volume, and this is the distance if you're looking at. So minimize the Z total cost subject to, yeah, we have this is the demand. Xij is the demand from individual place or the volume. So it should be more than the demand. Summation of xij from I to m. Xij should be more than the demand for all j 1 to n. Similarly, xij should be less than equal to total supply from the plant. So it should be less than supply and more than the demand of the distributor or the customer, and it should be less than equal to supply from the plant, because you cannot distribute or ship more than what is supplied, what is produced. Similarly, you have to at least distribute or ship what is more than equal to the demand of the customer. So you that meet all the demand, but you cannot ship more than what is produced. So these two constraints are depicted here. So these they become your constraint, and this is becomes your objective function when you talk about the optimization or the linear programming. And this is the non-zero. So all the shipment should be more than equal to zero, because you can not ship negative items, you have to ship zero or positive quantity. So characteristic of transportation mode is the value of technological coefficient and direction of inequality constraint. These are the two characteristics. Now let's look at one example. So the company called NXT is planning next month shipment from its 4 production plants to its 3 warehouses. And our goal is to minimize the total shipping cost. So there are 4 production plants and there are 3 warehouses. And we have to look at how to distribute from which production plant we should ship to which warehouse, so that our total shipping cost is reduced. And these plants, 4 plants, are located at Atlanta, Boston, Chicago, and Denver. And these are, you can see the shipment cost And of course, Atlanta monthly production capacity 75, at Boston 85, at Chicago 95, at Denver is 80. Similarly, monthly demand from warehouse is given here 90, 120, and 100. So constraint is the total demand, whatever you ship has to be more than this demand, and whatever you ship has to be less than equal to this production capacity of each plant, and similarly it has to be more than equal to the demand. So how to, this is the network model. I It gives you the different shipment cost from different, these are the four factories or production plant, and these are different warehouses. So you can see these are the, these are different nodes, these are different arcs, arrows and arcs, they show this. So this is the network model. So now let's look at how, whether we can solve in Excel, we can solve this thing in Excel. If we can, I can show you. Okay, the same thing you can see here. What I have done is same thing we've done in Excel. So these are different plants: Atlanta, Boston, Chicago, Denver, and these are three warehouses: warehouse 1, warehouse 2, warehouse 3. And monthly production capacity: Atlanta 75, Boston, Chicago, and Denver is written here. Similarly, the monthly demand from warehouse 1 is 90, warehouse 2 is 120, warehouse 3 is 100. It is given here. And then we create another matrix, same matrix as above, but here we will keep, let me keep all of them. Let me keep a random number here. Let me keep, say, 111 in each of them. Okay, now I want to minimize the total. Objective function is minimize the total shipment cost. Okay, and this is delivery. If you see, delivery is given here, it's equal to sum of from this factory to whatever shipped is total given here. From Boston, what is shipped is given summed here. So what total delivery from a plant is given by this column called delivered, and total what is received at different warehouse is given by this cell called received. This, so this row of received, it shows the different received quantity at different warehouses. Now this is my objective function. So this objective function basically is the total shipment cost, and I get, how do I get this shipment cost? Let me put the formula here. Product. First it will ask me. I'm looking at, okay, so my total objective function is, this is shipment cost and this is units. How many units? Yeah, decision in terms of units. So this become an objective function, which is sum product C5 to E8 and multiplied by C13 to C16. So now let me see if I can solve it using the solver. Yeah. So this is my objective function. I want to minimize this total shipment cost, that is the shipping cost multiplied by number of units, and then subject to constraint. So what is my first constraint? My first constraint is C17 to E17, which is given here. It has to be less than, it has to be more than equal to the demand here. And second constraint is whatever F13 to 6, yeah, here whatever is shipped has to be more less than equal to the production capacity. And I make this constraint non-negative. Select solving method as simplex linear programming. If you have some issues, then let me put this both the constraint here again for you. Okay, so both the constraints are come here. Now let me solve using solver. So I say keep solver solution. Now you see from Atlanta to warehouse 2 is 35, warehouse 3 is 15. Your number of units shipped from Boston, it is 85 units shipped to warehouse 2. From Chicago, it is 90 unit to warehouse 1 and 5 to warehouse 3. And from Denver, it is 80 to warehouse 3. So total, my total shipping cost would come out to be $10,025. And this is the minimum. I have minimized it. So you can see using this simple decision matrix and using the solver tool, I came up with the solution to this. Okay, how many given that minimizing total cost and given the unit, the shipping cost, how many unit has to be shipped from which factory to or which production plant to which warehouse. Now coming back, so this is the, so if we have to draw this is the final solution that we came, and we can again redraw it in a network, and this is the network diagram for the final solution. Now sometime we have shipment. Now we sometime we have transshipment where there is an intermediate stage where, for example, from this production plant, there are three production plants. Goods are shipped to four of warehouses. Sorry, five warehouses. So these are production plants. Given the distance, it is shipped to from three production plants. Goods are shipped to five warehouses, and from five warehouses, they are sent to six retailers. So these are our retail points from warehouse. So warehouse becomes intermediate. So it becomes transshipment. From to here to shipment, and from here to here it's a transshipment. So these problems are called transshipment problems. Now let's see how we can. Again, the issue is we want to reduce the total shipment cost. So you can see three plants are here. Plant 1, 2, 3. It is given things are sent to the five warehouses. We have their shipping cost and then monthly production. So whatever first constraint you can immediately see is that whatever we gonna be shipping or transshipping has to be less than the production, and of course it has to be less than the, is a total demand. It has to be more than the total demand from the retailer, not from the warehouse. So let's see, from warehouse to retail, this is the second stage. There are six retail stores and these are warehouses. Again, we have their shipping cost are given to us, and monthly demand from retailers is given to us. So that's, yeah, so it has whatever ship has to be more than equal to the monthly demand from the retailer and less than equal to the production from different three plants. Okay, now let's see if we can. So our equation, general formulation of transshipment model is minimize I to M summation K to L summation Cik into Xik plus Ki to L and Ji to N Ckj into Ykj. So you can see it's a summation first stage and the second stage. So both the costs are added and we are looking at the minimizing the total shipment cost of the stage 1 and stage 2 in this transshipment. And now we have, you can see there's a demand constraint. So this is objective function. These are the constraints. First constraint has to be more than demand equal to shipment most than equal to the demand. And then second constraint is it has to be shipment has to be less than equal to total supply from the production plant. And third is whatever is coming to the warehouse, we want to ship it. So we don't want to hold anything in the warehouse. We make sure that everything is shipped to the retailer so that it is there is no error in the warehouse stage, and it's most efficient system. And then we have non negative constraint here that whatever shipment is stage 1 and stage 2 number of unit has to be more than equal to 0. Now let's see if we can solve this thing again. We go back to Excel and let me see if I can solve it using Excel. So here is yeah, the same thing which is I showed you in the PowerPoint. Plant 1 to 3, warehouse 1 to 5, these are the shipment cost, these are production 470. Then from warehouse to retail, these are retail store, there's the total shipment cost, and then monthly demand. Now here is the how many units to ship. Decision variables, yeah, it becomes how many units to ship from stage 1, from which plant to which warehouse, and then from which warehouse to which retailer, right? So that we meet all the constraint, and our total production cost of stage 1, stage 2, which are number of units xik and ykj, number of units shipped, so that total cost is reduced. So let me write the objective function here. I put all of them here. Let me put one here. So you now you can see the objective function is here, but we have to find out how many units. So we gonna take help of solver, and in solver, of course, we want to minimize our objective function, which is the total cost, by changing the variable cell. So these are decision variables are k5 to 7, which I put all one. So maybe let me and subject to the constraint. First constraint is that our from first stage whatever we are getting in different warehouses from different plants, it is equal to k17, yeah, here. So both the this minus this equal to 0, yeah, that means both of them are equal. Whatever is coming to the warehouse is goes to the retailer. Second is our total Here production P11 to P16. Yeah, this has to be more than equal to H11 by 16 here, and our P5 to P7, which is the production. Yeah, total from plant 1, how much can be? It has to be less than equal to the production of different plants. So these are three constraints. We made them non-negative. Solving method is simplex linear programming. Then we click on the button solve. So as I keep solve a solution. Now you can see I have put all of them 1. Now they are changed. The values have been changed from plant 1 to warehouse 4. It is 100. From plant 2 to warehouse 2 is 150. Plant 3 to warehouse 1 is 140. And then from warehouse 4 to retail store 1 it is 80. From retail store 2 to warehouse 1 it is 40. From retail store 3 to warehouse 5 is 10. From retail store 4 to warehouse 4 it is 20. Retail store 5 to warehouse 100. Retail store 6 to warehouse 2 150. So you can see here, so all the constraints are met. Objective becomes the minimum cost is 17,800 while meeting the objective constraint, and these are the values of decision variables. So you can see using this is the network diagram of the final solution that we have got using the solver. So these are production plants, these are warehouses, and these are the retailers. And it shows how many units are shipped from which production plant to which warehouse, and then from which warehouse to which retailer. Sometime, okay, now the fourth topic is locating the service facilities. So now this is most common thing because we have so many service facilities that we think about much less expensive, and the number of instances when we decide on location of a new service facility is much more frequent than new factory or warehouse location decisions. So they normally will look for sites close to the customer, and location decision is closely tied to market selection because and then here the main thing is about maximizing profit, while in warehouse and warehouse or factory we are looking at minimization of the cost, production cost or shipment cost. But here the main decision when we're deciding on service facility is maximizing the profit. So for example, we have a case, we want to develop a model for locating a motel, and what is the objective function that we are looking at is dependent variable is, if you take it as simple multivariate linear regression, is a profitability. And then in this so multivariate dependent is profitability, then we look at category of variables or individual item category, like competition, what is the room rate, what are the rates of competitors, what like, then we look at demand generator independent variable like distance from military base hospital or the number of hospital or military base near it, how many colleges are near it, how many malls are near it. And then we collect, once we know what are the independent variables on which this profitability dependent variable depend on, then we collect the data on independent variable. So we look at, then we decide on we choose the variables that matter among this independent variable. So we look at correlation of profitability with all the potential parameter, and then we look at highly correlated independent variable. Then we run a regression with chosen independent variables, and profitability is a dependent variable. So for in this case, For example, when we ran the simple linear regression, I already done simple linear regression in my other presentation, where when I talk about forecasting, and we came up with the similar linear multivariate regression equation for forecasting. So use the same method of simple multivariate linear regression. We came up using Excel, Microsoft Excel, and Access Microsoft add-in. We have Access Analysis Toolkit. In Analysis Toolkit, we have this regression option available. Let me show you. So when I came here, for example, I have this, click on this add-in like solver. And how do we get this add-in is actually you have to go here, Microsoft file, you go to options, and then you have add-ins. You can see analysis tool package solver here. So I go to data analysis here, and I can see regression is one of the choices here. When I click on regression, it will ask for dependent variable, and then y is the dependent variable, and x1, x2, x3. You can choose as many independent variables, and then confidence knob 95 or 99, and you get the results, regression result. And suppose we use this and we run a regression, and I came up with this equation. So profitability is equal to a constant intercept plus minus 5.4 by state population per in plus 5.86 into room rate minus 3.91 square root income of the area plus 1.7 college enrollment. So you can easily see that what is the most important is you can hear which has a more impact on profitability is you look at the first positive, the room rate, and then you look at college enrollment. Then of course it also depend on something that is state population isn't something that is negatively impacting, and the income is also something that is negatively impacting. So then you decide on, so you then you put for different options. Suppose you have 5 location options. For each location you put these value, actual value of these independent variable, the actual data for this, and then you calculate p1. Suppose you have 5 things, so p1 to p5, find out profitability to each. And suppose for p5 it is the maximum, so you choose the one with the maximum profitability. So this is how you decide on the location of a service center or service facility. Okay, thank you very much. I hope you like this presentation. So I look forward to talking to you, sharing you more valuable and insights on the good topics related to business analytics. Thank you very much.